In this video, we'll talk about the error bound on Taylor series, which emphasizes why it is the best fit polynomial to a certain degree to a given function. So the idea here is we claimed it's the best fit polynomial to a certain function. How close is it? And do we have an idea of how this is going to change as I change the value of n, or how close I am to this point? And the answer is yes, and that's the sort of importance of Taylor's theorem, which we'll talk about a version of here that gives us this error bound. So we'll assume that I'm doing a nth order Taylor polynomial here, Tn of x, like we have down here. And we need to assume that one more derivative exists and is continuous. So the Taylor polynomial itself requires up to n derivatives. I need the n plus first one to exist and be continuous. I'm going to have k be some number that upper bounds that n plus first derivative between x, the point that I care about, and a, the center point of my polynomial. So here's my bound here that I get. Then I get the error bound. And the error bound says that the distance between my function value at x and my Taylor polynomial value at x is bounded by this k times x minus a to the n plus first power over n plus 1 factorial. Here's the main formula to know coming out of this error bound. Now, how can you interpret this? The main way you should visualize this is that if x is really far from a, this is a bad approximation. If x minus a is like 10, you're taking 10 to the n plus first power, which is huge. That's going to be a problem. However, as I take more terms, I will get a better approximation, ideally, because this n plus 1 factorial on the bottom is going to take it to 0. Instead, in picture form, we have the example here of cosine and its Taylor polynomials, which we could get from the Taylor series that we know. Here we have in a dashed blue line the graph of cosine of x. And then we have in the red lines on each image the increasing Taylor polynomials in different orders. So you have t0 in the first, you have t2 over here in the second, and then t4, t6, t8, and t10. The point here being, for all of these, once I get beyond 2 pi or so, these polynomials are terrible. They don't do a really good job of approximating the function because the polynomial is gone and being a polynomial, and the cosine function keeps oscillating, which you can't get by a polynomial. However, you can also see that as you take more terms in this series, you're fitting more and more of the curve, which makes sense because we know this Taylor series converges everywhere. So if I take enough terms, I should get really, really close to cosine of x everywhere with enough terms in the series. So as I add more and more terms, I should fit more and more of these bumps of cosine until I eventually cover as much as I want to get by a polynomial approximation. So yeah, in summary, far away is bad, but more terms let this work for a wider and wider range. And the main reason that works is because we know the Taylor series converges everywhere, so we should get that the polynomial is getting closer and closer to the series at that point. As an example of using this, let's find the error in approximating log of 1.5 by its fourth order Taylor polynomial centered at 1. So how are we going to do this? We're going to want to look at f minus t4 of x should be less equal this k that we have to find, x minus a to the n plus 1 over n plus 1 factorial. But in our case, n is 4. So this will be to the 5th over 5 factorial. And we want the error in log of 1.5. So we'll have x being 1.5 and a being 1. The error bound will tell us that f of 1.5, which will be log of 1.5, minus that polynomial at 1.5, is bounded by k times 0.5 to the 5th over 5 factorial. Now let's figure out what this k is. This k needs to be something bigger than the 5th derivative of f anywhere between x and a. The 5th derivative of u is bounded by k for u between x and a. So we need the 5th derivative. If our function is log of x, we can start taking derivatives. So f prime would be 1 over x, double prime, and we work this out until we get a 5th derivative. And we get the 5th derivative is 24 over x to the 5th. Now I need to find something that is bigger than this function between 1 and 1.5. Based on this function, because it's a 1 over power of x, it's going to be biggest at 1 because it decreases once I get beyond 1. So I can pick 24, this number up top, or the value when I plug in 1, to be my k. So I can take k to be 24, And if I do that, I get that the error between log of 1.5 and t4 of 1.5 is bounded by 24 times 0.5 to the fifth over 5 factorial, which ends up coming out to a 1 over 160, which in decimals is 0.00625. With the T4 approximation, you're within about 0.01 for sure of your answer. Your first decimal point is definitely right. Your second one might be, depending on what it rounds to. So this idea of what you can use for this error bound and how you might be able to use this sort of idea to talk about how close is my approximation, as well as to say, well, how many terms would I need to get to a good approximation of this function? Would it be substantially better if I took 5 terms? What about if I took 10 terms? Where do I need to be to get the error that I need to do my calculation with? And so that's where the error really comes into play, is when you want to approximate functions, figuring out how many terms you need and how much information you need to be able to get the accuracy you need to carry out your problem that you're trying to solve.